Welcome to Let's Get to the Marks, going through the AS Chemistry 2021 Paper 2 Organic and Physical. It's an hour and 30 minutes you've got. There's 8 questions that are long written answer questions, and then section B is the multiple choice. The code is 74042. I'll try and put the link to the paper in the description. Let's go. Question 1. Figure 1 shows the Maxwell-Boltzmann distribution of molecular energies in a sample of gas. So we've got the x-axis is energy. They want us to label the y-axis in figure 1. So pause the video, have a go. Okay, what you should label it here is number of molecules. And so the y-axis is number of molecules. State why the curve starts at 0. So what they're really asking you here is, how come when energy is at 0, there's 0 molecules? The idea is that all particles in the universe contain at least some energy. No matter how cold it gets, even at absolute 0, particles are not going to have 0 kinetic energy. So the only way you can have 0 energy is if you have no particles. If particles exist, even just one particle, then you must have at least some energy. So that's all we need to express here, that particles all have energy, so there must be 0 particles or 0 number of molecules when energy is 0. All right, let's look and zing on to the next question, which is 1.3. State what the letter X indicates on figure 1. So we need to look at figure 1 and what does the X tell us? So zooming in a little bit here. So what this peak on the Maxwell-Boltzmann distribution tells you is the most probable energy that any particle has at any one time. So it's the most probable energy held by a particle. And then for 1.4, the final part of the question, half of the gas molecules in the sample are removed. The remaining gas molecules are kept at the same temperature. Draw the new distribution of molecular energies for the remaining gas on figure 1. So if we removed half the particles, what would happen? We need to draw an exact identical curve, but half the size. Okay, that's not quite half the size, but they're going to give you the marks for that. And you do not want your lines to touch or cross at any point other than at the origin at 0, 0. They shouldn't ever meet again. And that will get you the mark. Right, moving on to question 2. Alkenes react with bromine, Br2. Name and outline the mechanism for the reaction of cyclohexene with bromine. So this is a 5 marker. They want the name of the mechanism and then they want the outline of the mechanism. So essentially, think about alkenes. They have an electron rich or an electron dense region, which is where we have the double bond. As a bromine molecule, which is non-polar, approaches that double bond, the electron repulsion from that electron rich region will repel the dot on the cross on the bromine molecule's covalent bond. The pair of shared electrons will be repelled away from the electron rich region, and this will polarize the bond. And so the bromine molecule becomes an electrophile because part of it becomes positive. So we call this electrophilic addition, because eventually those bromine atoms are going to add across where that double bond went. Now here's the mechanism. Always show your curly arrow going from a double bond to a positive. You should never draw a curly arrow going from something positive. It always has to be going from electrons. We also know that bromine's in group 7. It can only have one bond because it can only form one bond, obviously, because then it has a full outer shell. And so therefore it cannot have 2 bonds. So the bromine bond has to split. So you're going to get M1 for drawing the curly arrows, M2 for the splitting of the bond. And then in AQA, you don't have to show the delta positive and delta negative, but I like to do that anyway. The carbocation will get you a mark, so showing the positive charge on the ring. And then for the bromine negative ion, the anion, you've got to show the lone pair and the negative sign, and that will get you M3. And the final product you don't need to show in mechanisms. You don't, unless specifically stated. And this will get you 5 marks. You're going to get 1 for each of those, M1, 2, 3, and 4, and then 1 for the name of the mechanism, which is electrophilic addition. Okay, 2.2, explain why there is an attraction between a C double C bond and a bromine molecule. So I kind of already talked about this. Obviously, the carbon-carbon bond, the double bond, is electron rich, or you can say has high electron density on an electron dense area. Either way. Therefore, it how do we describe how it moves the electrons in the bromine covalent bond away from it? We say it polarizes the bromine bond. That's the shorthand using the correct terminology to describe that whole thing where the electron rich area, the cloud of electrons, repel the electrons in the covalent bond of bromine and push it away, making the first bromine atom positive and the second one delta negative. So we can just say, instead of having to explain all of this and say that these electrons are pushed away to the right hand bromine, we can just say the bond is polarized by the electron rich area. And that becomes delta negative, the top one, and the left hand one becomes delta positive. And now we can say the delta positive, or the positive bromine atom in the bromine molecule, is now attracted to the electron rich area, and that will get you all 3 marks. What happens then, it's important to say, you don't have to say this actually in this, but it's important to understand that the lone pair of electrons, although we have an electrophile, the lone pair in electrons, or sorry, the pair of electrons from the double bond go to the positive bromine. It's not the other way round. So yeah, and here we go. That will get you all 3 marks. Superbulous! Moving on to 2.3, draw the skeletal formula of the halogenoalkane formed when buta-1,3-diene reacts with an excess of bromine. So buta-1,3-diene, we want 2 double bonds. Let me just check. This is how I always check my carbons for skeletal formula. There we go. There's my buta-1,3 diene. Now, if it reacts with bromine and it says excess bromine, that means there's enough bromine to add across both double bonds. And so we've got to draw the skeletal formula of that. And I've done that right here. So all you want to do is get rid of the double bonds, stick a Br at each end of each double bond, so 4 BRs. Right, question 3. Propanone can be made by reacting propan-2-ol with an excess of acidified potassium dichromate 6. The propanone is removed from the reaction mixture by distillation. Figure 2 shows the apparatus set up by a student to make the propanone. By this method, the student clamps are used to hold the apparatus firmly in place. Okay, so here we've got the apparatus set up. There are 3 problems with the apparatus set up in figure 2. Identify the problem, describe the issue it would cause, and suggest how it can be solved. Right, so I'm going to write the answer up here so that I can explain it. And the first problem I see is they've got the water out underneath and the water in at the top. So problem 1 that I can spot is that the water should be coming in at the bottom. It isn't. The water's coming in at the top. The problem with that is just follow the water going down. If you follow the water going down, it's not going to fill that top first little centimeter of the condenser is not going to get filled. The water's going to come in and then just roll down to the right. So we're not going to ensure the complete filling of the condenser. And that means we won't get the most efficient heat exchange between the water in the condenser and the vapor inside the delivery tube. And what does that mean? That means that some of the propanone that we want to collect may come out as a vapor and escape. So essentially, we're not getting perfect condensation there. How should we correct this problem? We should reverse the direction of the water. So the water comes in at the bottom. That way it swells up from the bottom and it will completely fill the condenser. If it's coming in and going from bottom to top, it will completely fill the condenser and you will maximize the efficiency of the heat exchange. Ooh, there's problem number 1, and that will get you 2 marks. Excuse me, we'll have a little sip of water. Got dry mouth? Okay. Problem when you're talking all the time. I'm waffling like myself. Problem 2. So let's have a little look. Oh, look, there's no bung at the top. No bung at the top of the round bottom flask. What's the problem there? Some of our propanone is going to escape. Also, you should have a thermometer. Why should you have a thermometer if you have propan-2-ol and propanone there? Well, if I just boil it and heat it to whatever temperature I want, I'm not just going to get the propanone coming out there, but I might get some sulfuric acid vapor. I might evaporate some of the sulfuric acid. I might also evaporate some of my reactant, the propan-2-ol, and that might end up in there. So I'm not going to end up with pure propanone going into my test tube. I may be vaporizing some of that stuff, and it may be going up and traveling down the delivery tube. And without the bung, some of my propanone, some of my product's going to escape. So really, you've got two problems here. No bung means some propanone may evaporate and leave the round bottom flask, so we don't actually get to condense it. And then also, if I'm not keeping the boiling temperature just below or at the boiling point of propanone, so when you're doing fractional distillation, you should keep the boiling point at or just below the compound that you want to come out and distill off. And so here, you should keep the boiling point just below the boiling point of propanone, and you don't want it approaching the boiling point of like propan-2-ol, otherwise you're going to vaporize lots of propan-2-ol. You'll never get 100% pure. You're always going to have some vapor of propan-2-ol getting down here, but you want to keep it as far apart as possible. Now, problem 3, anti-bumping granules. They've not added anti-bumping granules, or not stated that they've added anti-bumping granules. So if you have no anti-bumping granules, you'll get large bubbles like I've drawn there in crusty blue. And what will happen there with large bubbles is they potentially break at the top of the surface of the liquid and spit liquid up, and that liquid will enter the condenser and contaminate your propanone product. So we don't want large bubbles, and so the way to solve this is to add anti-bumping granules. These will break up large bubbles. You'll only get small bubbles, and less of the liquid reactants will spit and fly up the tube, potentially entering the condenser. And so there you go. There's your 6 marks, and I've tried to put them in nice little color boxes. Let's move on. Right, 3.2. Another student completes the experiment using apparatus that is set up correctly. The student reacts 2 centimeter cubed of propan-2-ol with an excess of acidified potassium dichromate 6. The student obtains 0.954 grams of propanone. Calculate the percentage yield of propanone in this experiment. Give your answer to the appropriate number of significant figures. What am I doing? The moment I see mass, I want to do mass over MR times moles. And they've given me density. The moment I see density, I want to write out the density equation, which is mass over density times volume. So which one can I start with? What have I been given 2 of? Well, I've been given the density of propanol, propan-2-ol, and the volume. So straight away, the first thing that I can calculate is the the mass of propan-2-ol. So I'm going to do 2 for the volume times 0.786. Sorry, I haven't written that there. 0.786, and that is going to give me my mass of propan-2-ol. Now that I know the mass of propan-2-ol, which is 1.572 grams, I can take that mass over to the second triangle and do the mass of propanone over mass of propan-2-ol, sorry, getting confused, over the MR, and I can work out the moles. And once you know the moles of one, you can then work out your theoretical maximum moles, and we've got our actual mass. So let's do it. Okay, so the MR is 60 because CH3 is 15, CH is 13, CH3 is 15, so that's 30 plus 13 is 33. An H and an O, 16 is O, H is 1, that's 17. Add that together, totals up to be 60. So the MR of propan-2-ol was 60, so I want to do 1.572 divided by 60, and that is going to give me 0.0262 moles. And I've just calculated the moles of propan-2-ol. Now, it's a 1-to-1 reaction in the formation of propanone, and that means I should make 0.0262 moles of propanone. Now let's work back and find out what the maximum mass of propanone is that I should make, and I've been given the actual mass, which is 0.954 in the question. So it's a 1-to-1 ratio, so that means that we should make 0.0262 moles of propanone. Let's multiply that 0.262 by the MR of propanone, and if we add up the MR of propanone, we've got 15 each for the 2 CH3s, so that is 30, and then we've got 16 and 12 for the CO bond, that's 28, so the 58 is the MR. 0.0262 times 58 is 1.5196. I could round that if I like to 1.52 grams, or you could just leave it in your calculator as it is, totally cool. And now I want to do actual mass over theoretical maximum mass times 100. Bosh, percentage yield 0.954. divided by 1.52 times 100, and that should give me our percentage yield. And then we need to round to 3 sig, it says. So don't forget that. If you miss that out, you're screwed. So 62.76, we want to round to, oh no, it says appropriate number, not 3 sig. So I'm going to go just to 2 significant figures, 63%. And there we go. All 4 marks. Okay, let's move on to question 3.3. Keep moving on, keep moving on, keep moving on, keep moving on. Molecules of propan-2-ol and propanone each contain 3 carbon atoms. Suggest the shape and bond angle around the central carbon atom in each molecule of each compound. So let's look at propan-2-ol. The CH is the central carbon where the others come off of. So we're going to write CH3, OH, and CH3 coming off. Boom. Right, if you've got 4 pairs, you're like carbon atom, you're in group 4, you have 4 electrons in the outer shell, and those 4 electrons are all bonded. So you have 4 electron pairs all bonded around the central atom. This is the crustiest D-grade level GCSE art diagram you have ever seen. Okay, yeah, you're going to be tetrahedral. What's the bond angle for tetrahedral? It's 109.5. So let's look at propanone. Now we look at the central carbon atom in propanone. We've got a carbonyl go in there. We've got 2 CH3 groups coming off. Now you might say, yeah, isn't that 4 pairs of bonded? Yeah, it is. But because the double bond, they are all put together in one region, it's basically acting as 3 pairs. So it's trigonal planar and it has a 120-degree bond angle. Explain why propanone has the lower boiling point than propan-2-ol. 3 fat marks. Propanone, well, I can explain why. It's easier to explain why propan-2-ol has the higher boiling point. So propan-2-ol has the hydroxide bond, the OH bond. Of course, if you have NH, FH, or OH, you're going to have hydrogen bonding, and that's the strongest type of intermolecular force, and that's stronger than the intermolecular forces found between propanone molecules, which are dipole-dipole forces in the propanone molecules. So your 3 marks really are here for spotting that propan-2-ol has hydrogen bonding, then stating that hydrogen bonding is stronger than the intermolecular force in propanone, and the intermolecular force in propanone is dipole-dipole. So you get 1 for identifying the intermolecular force in each, so hydrogen bonding and van der Waals or dipole-dipole, and then saying that the hydrogen bonding is stronger. CFCs were used as refrigerants and in aerosols. The scientists Rowland and Molina published research in 1974 to show that CFCs are responsible for the destruction of ozone molecules in the upper atmosphere. A few years later, other scientists discovered that the concentration of ozone in the upper atmosphere was decreasing. In 1987, there was an agreement by many countries to restrict the use of CFCs. The molecule CFC11 was commonly used as a refrigerant. Use IUPAC rules to name CFC11. Once again, pause the video, guys. Have a go at the question on a scrap bit of paper, then unpause the video and check your answer against the walkthrough. So we need to ask ourselves, how many carbon atoms are in this molecule? There's only 1, so it's going to be a methane molecule, single bonds. There's 3 chlorines, so we use the trichloro, and there's 1 fluorine atom. So fluoro, put them in alphabetical order. Chloro, C before F. So trichloro, i.e. 3 chlorines. Fluoro, just 1 fluorine. Methane. So the answer to this is trichlorofluoromethane, and that is the name of this molecule. Of course, if you had to number, you would do 111 trichloro, 1 fluoromethane. But because there's only 1 carbon atom, we don't need to number it because there's no choice for another carbon atom. Now, coming down to this question, a molecule of CFC11 breaks down in the upper atmosphere to form a chlorine free radical. Write the equation. So we just need to write out our trichlorofluoromethane, so CCl3F. Ultraviolet light breaks it down in the upper atmosphere, and you're just going to split 1 chlorine atom off, give it an unpaired electron, which we show with a dot, and we have an unpaired electron on the fluorine as well. However, you could put these unpaired electrons anywhere on the free radical, so it could be before the C at the start. I like to put them at the end. And that's your mark for that. So let's move on to the next question. A typical refrigerator contains 0.50 kilograms of CFC11 with an MR of 137.5 one molecule of CFC11 causes the destruction of approximately 100,000 molecules of ozone. Notice what I'm doing here is I'm highlighting the units that you come across in these questions. Whenever there's going to be a calculation, you need to work out what equation you want to use. And we've got mass, we've got MR. So I'm pretty sure we're going to be doing mass over MR times moles at some point. Now, it's saying for every CFC, you break down 100,000 ozone molecules. Use these data to estimate the number of molecules of ozone that can be destroyed by 0.5 kg of CFC11. Give your answer in standard form. We are also given Avogadro's constant, which means you're going to have to use that as well. So my first, even if you can't work out what you've got to do here, first thing to do is say, well, I've been given M and MR. Let's work out the moles of CFC. So I've got 0.50 kilograms. What do we need to do to that? So we times by 1,000, we get 500 grams of CFC divided by the MR of CFC, which is 137.5. And that's going to give us N, which we use for the number of moles. And the number of moles is going to be something like 3.63. We could round that to 3.64 if it's bigger, and it is, because on my calculator it's 3.636363. So I'm rounding it to 3.64. That's the moles of CFC. So you've at least scored a mark here working out the moles of CFC. Now we want to know how many molecules of CFC do we actually have? So how many molecules of CFC do we have? Well, we're going to do number of moles times L, which is Avogadro's constant, and we'll find out how many moles. So there's 6.022 times 10 to the 23 particles of CFC in 1 mole. So we go 3.64 times Avogadro's constant. I'm using L here, and we get 2.19 times 10 to the 24. Now, what I also need to take account of, that's the molecules of CFC, but the ratio of CFC to ozone that's broken down is 1 to 100,000. So I need to times that by 100,000. So timesing it by an extra 5 zeros, so I can just add an extra 5 on there. So 2.19 times 10 to the 29. And that is the number of molecules of ozone that will be broken down by 0.50 kilograms of CFC. Okay, moving on, state the benefit to life on Earth of ozone in the upper atmosphere. What is the ozone for in the upper atmosphere? It absorbs harmful ultraviolet radiation, which is going to reduce the amount of skin cancer, reduce the amount of harmful UV radiation reaching human beings on the Earth's surface, essentially. You can say blocks UV light if you like. Suggest one reason why the use of CFCs were not restricted several years after Rowland and Molina published their research. Obviously, maybe we could say more evidence was needed, still needed to be reviewed by peers. Industrially, CFCs were the only thing that could be used in fridges. People weren't ready to give up fridge use yet until they found an alternative chemical to replace the CFCs in fridges and in aerosol cans. There's loads of different answers there. CFC is a greenhouse gas. How can that contribute to global warming? So really, this is a 2-marker. And molecules that contribute to global warming are polar molecules. That means they have a delta positive atom and a delta negative atom. And CFCs obviously have fluorine and chlorine, which are electronegative, and carbon, which is slightly electropositive. Therefore, if you have a polar bond, it will vibrate and it will absorb infrared radiation at a similar wavelength to the vibrations or oscillations of that polar bond. Non-polar bonds, by the way, like carbon-hydrogen bonds, don't really absorb infrared radiation because they're non-polar and they don't vibrate in the same way that polar molecules do. Question 5 is about polypropene. 3 key steps in the manufacture of polypropene from crude oil are shown. We've got crude oil, step 1 going to naphtha, step 2 to propene, step 3 to polypropene. Naphtha is a mixture of alkanes with 6 to 12 carbon atoms per molecule. For each step, name the process and briefly the purpose of the process that leads to the formation of polypropene. Pause, have a go. Right, so first of all, we're going to do fractional distillation on crude oil, and that is going to separate your hydrocarbons into the different fractions. But they're really testing you on what is a fraction. So a fraction is a group of hydrocarbon molecules that have similar chain lengths, hence similar boiling points, so they condense at the same part of the tower. So naphtha is not just one hydrocarbon like octane, it's actually all hydrocarbons from 6 to 12 carbon atoms. All alkanes from 6 to 12 carbon atoms. So like heptane, nonane, those would all fall in the naphtha range. So fractional distillation separates compounds into molecules of similar size and boiling point. Now, for the second part, how do we get naphtha and make it into a smaller molecule like propene, which only has 3 carbons? We have to do thermolytic cracking, so we can make smaller molecules from longer molecules, longer hydrocarbons into smaller ones, or longer hydrocarbons into alkenes, hence propene. Then step 3, we want to take propene and turn it into polypropene. That is called addition polymerization. And what we do there is we take the monomers, the small alkenes, and we join them together. High pressure, catalyst, whatever you need for that. But we don't need to state that here. We just need to say addition polymerization. And the purpose is to take small molecules and join them together to make a long molecule, a polymer. So join small alkenes or monomers together to make a polymer. Right, 5.2, polypropene is not biodegradable because it is unreactive. Explain why polypropene is unreactive. Well, if you look at the bonding in an addition polymer, they tend to have carbon-carbon bonds or carbon-hydrogen bonds, CH bonds or CC bonds. Here is my polypropene. And essentially, these bonds, what do you notice about carbon-carbon and carbon-hydrogen? They've got similar electronegativity, the carbon and the hydrogen, and carbon the same. So they're non-polar bonds. If they're non-polar, they're neither going to attract positive cations or negative anions. They're not going to attract electrophiles or nucleophiles. Hence, they're not very reactive. So we can say the fact that the bonds are non-polar, carbon-carbon, carbon-hydrogen, means they're unreactive. This next question is basically saying, why is it beneficial to have biodegradable plastic, biodegradable polymers? Obviously, if we have biodegradable plastics, less of our rubbish goes to landfill sites because it will break down naturally in the environment. Okay, question 6. This question is about 2 experiments on gases. In the first experiment, liquid wire is injected into a sealed flask under vacuum. The liquid vaporizes in the flask. Table 2 shows the data. So straight away, the fact that you've been given R equals 8.31, it tells me we're doing the ideal gas equation because they're giving us the gas constant. So we want to do PV equals nRT. There's some other elements that tell us that as well, the fact we've been given pressure and volume. So I want to rearrange that to find N because we're looking to calculate the relative molecular mass. We know that mass over MR equals moles. So I'm going to get the N for that and I can work out the mass because it's been given to me in the table. So I just want to substitute in PV over RT equals N. So I want to do 51,000 because pressure should be in pascals in this equation. And I've done 482 times 1 times 10 to the minus 6. I'm going to change that. That looks so ugly and messy. Okay, now you can do this 2 ways. You can either take 482 centimeters and to turn into meters cubed, we can divide by 1,000,000. So divide by 1 times 10 to the 6. I've times by 1 times 10 to the minus 6, which is the same result and just a bit easier to write in the working out. Put that over the top of 8.31. The temperature is already in Kelvin, so we can keep it as 297. And if we do that, smash it in the calculator, we get 9.96 times 10 to the minus 3 moles. Now that we have N, the moles, we take it upstairs to the mass, which is 717 milligrams. Need to turn it into grams, folks, so divide by 1,000 to get 0.717. Mass over moles gives me 71.98, but we've been asked, circled here, for the relative molecular mass. Relative molecular mass is a whole number. So therefore, I need to convert this to a whole number. 71.98 is closer to 72 than 71, so the answer is 72. And there you go. Boom! 6.2, in the second experiment, another flask is used for a combustion reaction. Remove all the air from the flask. Add 0.001 mole or 224 trimethylpentane to the flask. Add 0.02 mole of oxygen to the flask. Spark the mixture to ensure complete combustion. Cool the mixture to the original temperature. We have an equation. Calculate the amount in moles of gas in the flask after the reaction. Right, I know I got 0.001 moles of C8H18. What I need to do is work out how much oxygen has been used up and what my excess oxygen left over is. We're going to have none of that C8H18. It's completely combusted, right? They've told us that in the question. So we're going to have none of the 0.001 left. But I want to know how much more oxygen is going to be left over. So I'm going to do 0.001 times 12.5, and that gives me 0.0125 moles of oxygen unneeded. How much oxygen did we have in total to start with? It tells us in the question we have 0.02 moles of oxygen in the flask. So we know all the C8H18 has gone, but not all the oxygen is left. So we're going to do 0.0200 moles of oxygen minus the 0.0125 moles of oxygen, and that's going to tell us how much oxygen gas is left over at the end, and that's part of our mixture of gases that are left at the end. So we got 7.5 times 10 to the minus 3 moles of oxygen left at the end. Now let's look at the other gases left at the end. Well, we got liquid water, not a gas, so we don't need to look at how many moles of water are made. But we've got carbon dioxide, so that is a gas. Now that is 8 in a ratio of 8 to 1 with the C8H18. So what we want to do there is go 0.001 times 8, and that gives us 8 times 10 to the minus 3. And I want to take my moles of carbon dioxide left over, my moles of the excess oxygen that was left over unreacted, smash them together in the calculator and get my final moles of gas that are left over. And it's 0.0155. Okay, moving on. So we're on question 7. Prop-2N1-ol is a natural chemical found in garlic. It's also used in the production of plasticizers. Prop-2N1-ol can be prepared by reacting 3-chloroprop-1-ene with a dilute aqueous sodium hydroxide. Name the mechanism for this reaction. Well, let's take a quick zing and draw it out and see if we can work out what the mechanism is. So here I am drawing I'm not going to put the chlorine there. Let's put it on the side. Makes it a bit easier. That's going to be delta negative. The carbon's going to be delta positive. There we go. I've put an extra hydrogen on there. What an idiot. Never mind. But essentially, the hydroxide ion is attacking that delta positive carbon. So what do we call negative, well, an anion that's attacking something positive? We call it a nucleophile because it's hunting out, it's attracted to positive things. And of course, this is swapping. The hydroxide's joining, the chlorine's leaving, so it's substitution. This is nucleophilic substitution. Right. 7.2, prop-2N1-ol can also be formed from blah, 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 blah. What's that? That's a diol. The presence of an acid catalyst. Name and outline a mechanism for this reaction using an acid catalyst with propan 1,3-diol. So what we need to look at here is that you've got one reactant and you're forming two products. What does that tell you? If you start with one thing and you end up with two things, it means something has been eliminated. Of course, the other way around, if you started with two things and ended with one, it's addition. And if you start with two reactants and end with two products, that's substitution because you've not made anything extra. Okay, let's sing down. We now know it's an elimination mechanism. So let's get in and do the mech. So we want to attack one of these alcohols, and you've got the lone pair on the first hydroxide I'm going to do, and the curly arrow is going to the hydrogen ion. Remember, this is an acid elimination. So that is going to get us M2. What is M1? That was the name, elimination. So now we've drawn the extra hydrogen on. Just whack all these atoms together. That is an oxonium. It's now got, whenever you get 3 bonds around an oxygen, you put a plus sign on it, so that's an oxonium. That means that the bond here, the bond between the oxygen and the carbon, is going to donate its electron pair to get rid of that positive charge, and so we're going to eliminate water, hence the name of the mechanism is elimination. That gives us the M3 mark. Now let's draw the intermediate where we have a carbocation, because we've now got a carbon atom with only 3 bonds. That has a positive charge, so that's called a carbocation, and it's a hydrogen that's adjacent to the carbocation that donates its electrons to stabilize the bond, and it forms a double bond there. And there we go. That's your M4 for the correct carbocation with the arrow from the adjacent hydrogen there. And I've circled the hydrogen because, of course, that reforms the catalyst. Hence, why the hydrogen ion is a catalyst and an acid catalyst is because it reforms at the end of the mechanism. Let's move on to 7.3. Prop-2N1-ol forms an addition polymer. Draw the repeating unit of polyprop-2N1-ol. So what I want to do is draw out the prop-2N1-ol. So here we are, is prop-2N1-ol. So we're doing that there, bosh, bish, bash, right? Now, what we want to do is show how you draw the polymer from this. So always circle your double bond because that is the bit that's going to go inside the brackets. Now, you don't necessarily have to draw the brackets at A level, but I think it's a great way to think of it. So the bonds extend outside the brackets and are left open-ended, and you draw the brackets, then you know everything else has to fit above and below those two carbon atoms. So I can stick the first two hydrogens above and below, that hydrogen there, and then I want to circle this bit with the alcohol and the CH2 group, and that's basically going to go, well, it's kind of going up there, but if I bend it round, it's bending round and going above the double bond. So it's going over here. And that is how you draw it. I like to put the brackets there. It helps me make sure I know nothing else is to attach either end of the original carbon double bond. And you can put an N there if you like. That's old GCSE styley. Right. Move on to question 7.4. Figure 3 shows the infrared spectrum of a functional group isomer of prop-2N1-ol. The isomer reacts with acidified potassium dichromate 6 to form a green solution. Draw the structure of this isomer. So let's get up that structure again of prop-2N1-ol. There we go. This is the thing we want to get the isomer of. Now we know that dichromate 6 went green. What does that tell us? It tells us it's an aldehyde. So it starts orange, then it goes to those Cr3 plus ions that give a green color. And so we know it's an aldehyde. So I'm just going to draw the most obvious aldehyde, propanal, and then check all the carbons and hydrogens fit in because we've got 3 carbons there. We know it's an aldehyde, so we zing through and then just double check, make sure we've got all the same atoms. So I've got 6 hydrogens, 1, 2, 3, 4, 5, 6, yes, 3 carbons, 1, 2, 3, 3 carbons, got an O, bish, bash, bosh, it's done. Let's move on to the last question before the MCQ.
This question is about enthalpy changes. Define the term enthalpy change. So the enthalpy change is this symbol. So they're saying, what is the definition of that symbol? And it is, you just have to learn this one off by heart. The heat change at a constant pressure. And that you just have to learn off by heart. That's a revision card job. So make sure you know it. Comes up quite a lot in AQA and in other exam boards. Right, now we've got a little bond enthalpy one, which is always nice. So let's go through this one. Propane undergoes complete combustion. We've got 1 molecule of propane plus 5 oxygen molecules goes to 3 carbon dioxide molecules and 4 water molecules. We have the enthalpy change is minus 2046 kilojoule per mole. The table below shows some bond enthalpy data. So we've got the mean bond enthalpy for the carbon-hydrogen bond is 412. The mean bond enthalpy for the carbonyl bond is like 743, or the COO bond. Then we got the OH bond, 463. The bond enthalpy for oxygen, for an oxygen bond, is 496. And we've got the vaporization, which is a water molecule going to 1 water molecule in the gaseous state. The enthalpy of vaporization is plus 41 kilojoule per mole. Use these data to calculate a value for the CC bond enthalpy in propane. So what you're going to get the marks for really here, he says, you kind of want to set out your reactants, find all the total enthalpy of the bonds that you've been given the data for the reactants, going to get a mark for that, and then write down the total energy in the bonds that are released in bond making, and that's your products over here, and then set that out in an equation, put a minus in between them, equals that, rearrange to find the missing bonds. So let's have a go at that. So first of all, we've got propane. Good thing to do is just draw a little like displayed formula for propane. What you can do from that, you can work out how many CH bonds there are. So 1, 2, 3, 4, 5, 6, 7, 8. So I want to do 8 times 412, and that comes to 3296. And then we don't know these two CCs, so we've got like 2 times CC that are unknown. But then we do have 5 oxygen molecules. So 5, we want to add the 8 times 412, and we want to add that to 5 times 496. Some people get a bit confused when they see a double bond there and they do something silly there. You don't need to like multiply it because there's a double bond. So we want 5 times 496. Now 5 times 496 comes out on the calculator as 2480. Of course, you can just put this all on your scientific calculator, add these two together, and you're going to score your first mark for adding these two together. So it's for the reactants, we have 5776 added to our missing 2 CC bonds that we carbon-carbon bond that we do not know the answer for. So that's our total over here on the reactant side. Now let's do the product side and work out what we've got going on there. So I've got 743 for carbon dioxide, but obviously carbon dioxide has 2 CO bonds within it. So I want 6 times CO2. So let's do 6 times 743 because we've got 3 carbon dioxide molecules, each one with 2 CO bonds. So 6 times 743, 4458. I want to add that to 4 water molecules, which means I'm going to have 8 lots of OH. So add that to 8 times 463. Where was I? Sorry, pause there. 8 times 463, that equals 3704. So that covers our carbon dioxide and water, but we now have to take account of the vaporization enthalpy over here from the liquid water turning to gas, or the other way around, the gas water condensing to that. So what I'm going to do is plus 4 times 41, and that gives me 164. And what we're going to do, we're going to smash all of those together to make our products total is going to be 8326. Now, I like to, like I said here, put a minus where this arrow is. So you see there'd normally be an arrow between the reactants and products. I put a minus now, and then equals minus 2046. And then you just got to rearrange that to make 2cc the subject. So, for example, let's start by minusing 5776. We could start with that from each side. So let's minus 5776 from each side, in which case we're going to get what's going on over here? Right. In which case we're going to get 2cc minus let's take 5776. So 8326 minus 5776 equals I can't even see properly. 2550. I've got the sunlight in my eyes. So 2550, and that equals minus 2046. So now what I want to do is add, let's add 2550 to each side. And if we do that, running out of room, if I add 250 to each side, I'm going to get 2cc is equal to 504. So I want to find out what 1cc is. So I'm going to divide that by 2. And we're going to find that this equals 252. And that is your lovely jubbly answer, 252. And that's the mean bond enthalpy in kilojoule per mole for the carbon-carbon bond. So, wunderbar. Hopefully you found that all right. Right, let's move on. Let's go. Explain why the value given for the OO bond enthalpy is not a mean value. So you might have noticed during this question, a little bit strangely, but you might have noticed that the bond enthalpy for oxygen is not in the table with the other bonds. You might say, well, why isn't there bond enthalpy for oxygen? You can't have a mean bond enthalpy for oxygen. Remember, this bond, oxygen, where the hell is my pen? Here it is. The oxygen is in group 6. It can only have 2 electrons in the outer shell. It can only form 2 bonds. So if oxygen is bonded to itself, it cannot bond and be part of another molecule. That is impossible. So the only place you will ever find the OO double bond, the oxygen double bond, is between itself in an oxygen molecule. So there's no such thing as a mean bond enthalpy for oxygen, because the only time you will find that bond is in oxygen. It's not found in any other compound, that bond. So we can't work out a mean bond enthalpy for that. Okay, coolio. Let's just put that down as our answer. So we want to say OO bond only found in oxygen, not in any other substance. So there is no mean bond enthalpy. Remember, the mean bond enthalpy is the mean bond enthalpy for that particular bond from a range of different substances, and there is not a range of different substances for the oxygen bond. Right, that's the end of question.
All right, question 9. Which alkene shows EZ isomerism? So EZ isomerism requires you to have a double bond. And then the carbon atoms on the double bond, each carbon must have 2 different groups attached. Now, you're not looking at the sides of the carbon atom. It's fine if they have the same group on one side of the carbon atom. Of course, that's cis, or that is Zuckerman, Z isomerism. But we're talking about each carbon atom above and below must have a different group opposite. So what we're looking at for EZ isomerism, let's try the first one, 2,3-dimethyl-butene. Can this have EZ isomerism? So we've got we've got the 2-ene, the double bond on the second carbon. Now we're going to put a methyl on the second and a methyl on the third. Now look, oh, another methyl on the same carbon. So this can't be, and another methyl on the right-hand carbon of the double bond. So they've got identical groups on the carbon atoms. They cannot do EZ isomerism. Now, 4-methylpent-2-ene, let's draw this out and see if it can do EZ, and if it can do EZ, then it's our answer. So we're going to put the double bond on the second carbon again, and then we're going to count 4. I'm going from right to left here. It doesn't really matter, but and that's my methyl group. So the first carbon atom has all of this attached as one of its groups and a hydrogen as the other group. And then this carbon atom has a methyl and a hydrogen. So yes, each carbon has 2 different groups attached. It doesn't matter that there are 2 hydrogens there. They're attached to different carbon atoms. So that's the correct answer. And we don't need to look at C and D then. Let's go to 10. A compound contains 40% carbon, 6.7% hydrogen, and 53.3% oxygen by mass. Which could be the molecular formula of this compound? So what I want to do is work out the empirical formula first. You know how to do that. You do the percentage over the relative atomic mass, or the AR of the element. And then you simplify it into the simplest whole number ratio, and then any multiple of that could be the molecular formula. So we're going to get 3.3, 6.7, 53.3 divided by 16. That's going to be 3.33 again, roughly. And then if we divide these all by the smallest, 3.33 is the smallest number there. So we're going to get 3.33 over 3.33, 6.7 over 3.33, and 3.33 over 3.33. We're going to get a ratio of 1 to 1. Which one is a multiple of that? Well, not the first one, not that one. We can see here answer C is a multiple, isn't it? Because if you times this by 2, you get 2, 4, 2. So any multiple of our empirical formula could be the molecular formula, and that's the only one that's a multiple of the empirical formula. So there we go. Right, 11. When driving a car, a legal limit for ethanol, molecular mass 46, is 80 milligrams per 100 centimeter cubed of blood. What is the concentration in moles per decimeter? So we need to convert our 80 milligrams per 100 centimeters just into moles per decimeter. couple of ways you can do this. We could have just done, anywho, this is the way I'm going to do it. So there's a number of ways you can do this, but I'm converting the 80 milligrams to mass. So we've got 0.080 grams, dividing it by the MR, and that is going to give me my number of moles. And my number of moles is 1.74 times 10 to the minus 3. And that's how many moles are in 100 centimeters. So how many moles would be in a decimeter? A decimeter is 1,000 centimeters. So 1,000 divided by 100 is 10. So times it all by 10. And I'm going to get 1.74 times 10 to the minus 2. Now, we could have used the mole volume and decimeter calculation, or the mass over concentration times volume calculation as well. But this is the way I did it. I just did it mental math style. Right, let's go to 12, which is a propagation step in the chlorination of methane. Listen, when you're looking at steps of the free radical substitution business, get rid of anything that has a hydrogen free radical in it. That is not going to be applicable. And look, C, is that propagation? When you get two free radicals together? No, that's termination. Two free radicals coming together and not producing another free radical is a termination. All these other three steps are propagation because free radicals are formed, but you don't get hydrogen free radicals in the chlorination of methane. So you can immediately get rid of those two, and D is the correct answer. Obviously, you do get methyl free radicals formed. 13. Which compound is not formed by reacting 3-bromo-3-methohexane with warm ethanolic potassium hydroxide? So what you'll see for A, B, C, and D, they're all alkenes. And we've got an elimination reaction going on here. So the key is, where does the double bond form? The double bond can form either side of the bromine atom that's attached in this reaction. So the double bond will form either side of the bromine atom. And so what we want to do there is make sure that this product can be formed or cannot be formed either side of where the bromine's attached. So wherever you see the bromine attached, the double bond can form either side. So the only one here that cannot be formed is B, 3-methohex-1-ene, because you won't get the bromine formed. You won't get the double bond formed either side of the bromine and end up with 3-methohex-1-ene. Okay, question 14 to 16 refer to the reaction of 1-bromopropane with a solution of potassium cyanide in aqueous ethanol. What's the organic product of this reaction? So what we got going on here is we've got nucleophilic substitution. That the potassium doesn't get involved as a spectator, but the cyanide, the Cn minus with the lone pair, is acting as a nucleophile, attacking that delta positive carbon, which means that the bromine is going to snap off, and we're going to extend the carbon chain. So could you have propylamine? No, we're extending the carbon chain. It's going to have 4 carbons, so it has to be B or D, right? So maybe it's butane nitrile, or is it butyl amine? Well, it can't be butyl amine because that would have NH2. Nitrile is what we call the CN. So D is the correct answer. Now 15, which is the minimize this so we can get it all in the shot, which is the correct mechanism for the reaction. So there's something wrong with 3 of these, and this one is missing a negative sign on the nitrile, so get rid of that. That one has got the sign and it's attacking the carbon, and the bromine's breaking off in the right way. That's correct. B's correct. Why is C incorrect? Once again, it's missing the negative, and then D's a little bit confusing, but basically they've put the lone pair on the end, so you could say, oh, they're not happy with that, and that could be our reason for D being the incorrect answer. What are we on? 16. Right. The reactions of 1-bromopropane and 1-chloropropane with potassium cyanide, aqueous ethanol, occur at different rates under the same conditions. Which row correctly shows the compound with the faster rate of reaction? The correct reason for this. Right. So 1-bromopropane is going to break down faster than 1-chloropropane. And the reason being the carbon-bromine bond is weaker. It has a lower bond enthalpy. The mean bond enthalpy of the CBr is lower than the CCl, and it's nothing to do with the polar nature of the bond, because the CCl bond is more polar. You'd think it'd be attacked more, but it actually comes down to bond enthalpy. 17. Which compound has a molecular formula that is different from the others? So we want to calculate their molecular formulas roughly. 4 carbons. What's that? 4 times 12 is 48, plus 2 oxygens. or whatever. We don't need to add up the MR. So it's C4H6O2, roughly. This one is C4, yeah, and then there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 hydrogens here and 2 oxygens. So these two do not have the same formula, B and A. Now let's see, one of these is going to be the same. So this has 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8. So that means that, yes, the top one, C4H6O2. So A is the one that is different from all the others. Look, we can check the bottom one out as well. We can check D out. So if we check D, it's got 1, 2, 3, 4 carbons. There's 3 hydrogens there, 1 there. There's 1 on the OH. That's 5. 1, 2, 6, 7, and then 1 on the aldehyde group 8. Yeah. So that should be C4H8O2 again. So yeah, and yeah, A is correct. C4H6O2. That is the formula. The rest have C4H8O2 or something like that. Okay, 18. Which compound reacts with hydrogen bromide to give 2-bromor-3-methabutane as the major product? So what you want to do when you're sorting out who's going to be major, who's going to be minor, is how many alkyl groups you'll have. So I'm going to go straight to the correct answer here. It's D. And we'll look where the double bond is. The double bond, it's either going to form we're either going to get 2 bromo or like 1 bromo 3 methabutane here. If we look at the double bond, what's going to happen here is, hold on, let me redraw this out. Let me draw. Actually, save time. Not going to draw it. I'm just going to come down to D. Right, look. If the bromine attaches here, you'll have an alkyl group here, and this will gain a hydrogen and become CH3 because the double bond will go. So it'll have 2 alkyl groups, stabilizing the carbocation, making that more likely to be the major product. However, if the bromine atom joins here, the carbocation that will form that version will only have 1 alkyl group, and so will be less stable. So that carbocation is much less likely to happen. The bromine is much less likely to join on to the first carbon. It's much more likely to join on to the second carbon and form D. So 19, which statement is not correct about the industrial production of ethanol from ethene at 300 degrees? The reaction is catalyzed by an acid. Yes, phosphoric acid, isn't it? The reaction has 100% atom economy. Yes, look, you only make 1 product, so it's got to be 100% the atom economy. Which is not correct. Oh, geez. Sorry, that's correct. So that's not true because that's incorrect. Yeah. An increase in temperature decreases the equilibrium yield of ethanol. Well, we've got to look. It is exothermic, minus 46. That's exo. And I think of that as the hot side to the reaction. And that means that the left-hand side or backwards is cold. It's endothermic. If you increase the temperature, the equilibrium will shift to the cold side. Le Chatelier's principle, it will oppose the change. So it will try and absorb the extra heat and it will go to the endothermic side. So that is true. So that's also incorrect because that would decrease the yield of ethanol. And then D, an increase in pressure increases Kc. What do we know about pressure and concentration and Kc? Both pressure for gas reactions and concentration for like solution reactions do not change Kc's value. And why? Because when you change the pressure or the concentration, the equilibrium will shift and the ratio will end up being the same as it was before. The ratio of products over reactants will end up exactly the same as it was before. So our incorrect answer is D, and that is the correct answer because we were searching for the incorrect one. Okay, let's look at 20. Which statement about the use of a catalyst in a reversible reaction is correct? The activation energy for the reverse reaction is increased. Now, you don't increase the activation energy. Of course, catalysts lower the activation energy. Catalysts also don't affect the equilibrium constant Kc. They do allow you to achieve equilibrium faster because we increase the rate of reaction. Both reactions, both the forward and reverse reaction, increase, and so you reach equilibrium faster, but it doesn't affect the position of equilibrium, so it won't affect Kc. And the enthalpy change for the forward reaction decreases. No, catalysts do not affect the overall enthalpy change, they just lower the activation energy. Right, we have an excess of magnesium reacts with hydrochloric acid to form hydrogen gas. Line X on the graph shows how the volume of hydrogen produced changes with time as magnesium reacts with 30 centimeter cubed of 0.1 mole per decimeter hydrochloric acid. The reaction is repeated using 20 centimeter cubed of 2 mole per decimeter hydrochloric acid with all the conditions the same. So what I want to do is use N over CV and work out how many moles I have of each acid, and therefore I'll know how many moles of hydrogen gas are being released. What's the maximum amount of product? So with the first reaction, we produce 0.03 mole. And with the second reaction, we're going to, when I said produce 0.03 mole, we don't actually produce 0.03 mole. You produce, is H2, but never mind. That's how much acid we have. With the second reaction, we have 0.04. So it's a third bigger, not a quarter. Why did I write a quarter? What an idiot. Right. It's a third bigger in moles than the original, right? So we have, as it's a third bigger, a third amount more moles, it's going to react faster, more collisions, etc. And so that's why we had a steeper curve for B. Right, which statement is not correct about the pollutant sulfur dioxide? It can be removed from car exhaust fumes by a catalytic converter. It can be removed from power station flue gases with a reaction with calcium oxide. Yes, it's an acidic gas and it gets neutralized by the base calcium oxide. It can cause respiratory problems. Yes, an acid rain, it forms sulfuric acid in water. Cannot be removed with catalytic converters. They specialize, the platinum or palladium catalytic converters specialize in removing nitrogen oxides or by turning them back to nitrogen and oxygen or removing unburnt hydrocarbons. Right, what is the percentage atom economy for the production of ethanol from glucose? So this is the final question, and all I got to do here is do 2C2H5OH, 2 molecules of ethanol, over the total product, so over 2CH5OH plus 2CO2. So I want to work out what the MR of glucose is, and it's 46 times 2 is 92 because we've got 2 glucose. So I'm going to do 92 over 2 glucose plus 2 carbon dioxides, which is 92 plus 88, which is 180. So 92 over 180 times 100 is just over 50%. It's going to be 51.1%, roughly speaking. All right, guys. Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the mark.
You're still here? It's over.